Skoda can now offer its customers even more choice when selecting a new car. For drivers who require a vehicle which is extremely economical and yet powerful, Skoda have introduced a 1.9-litre diesel engine for the Felicia. This compact engine, which has an output of 47 kilowatts and develops 124 newton-meters of torque, features exhaust gas recirculation and a catalyst to reduce emissions. The diesel engine provides good performance for the Felicia. It can accelerate to 100 kilometers per hour in 16 seconds and has a top speed of 150. Its fuel economy is equally impressive, 6.3 litres per 100 kilometers consumed in the urban cycle. And only 4.3 litres are used at a constant 90 kilometers per hour. This video describes the engine's main features and is aimed at helping technicians understand its operating principles and repair techniques. More in-depth information is available in the self-study book number 13 and the repair manual. The tape is in 4 sections. Section 1 looks at the basic diesel principles. Section 2 describes the main mechanical features and repairs which are different to previous petrol engines. And Section 3 covers the engine's control or management system. Section 4 looks at the fault diagnosis aspects. To help you locate items if you need to review them at a later date, there's a counter in the corner of the screen and an index on the video cover. The diesel engine, invented by Rudolf Diesel over 100 years ago, is highly efficient. So let's begin by finding out why. In the petrol engine, an air-fuel mixture is compressed by the piston and is then ignited by the spark plug. The engine's output is controlled by the throttle valve. At full throttle, the cylinders are filled with an air-fuel mixture, allowing the engine to develop maximum power. In part-load conditions, the throttle valve restricts the quantity of mixture flowing into the cylinders, and consequently, the engine's output is reduced. Unfortunately, this throttling of the intake to control the engine's output also has the effect of reducing the volume of mixture filling the cylinders. This, in turn, lowers the compression pressures and reduces the engine's efficiency. In the diesel engine, only air enters the cylinders. The air is compressed into a much smaller space than that of the petrol engine. A compression ratio of 23:1 is quite normal for a diesel engine in comparison with, say, 9:1 for a petrol engine. By compressing the air so much, it becomes very hot, usually reaching 700 to 900 degrees Celsius. Into this hot air, atomized diesel fuel is sprayed by the injector. The fuel is ignited by the heat and consequently burns. Like the petrol engine, the expanding gases force the piston down the cylinder on its power stroke. In the Skoda engine, the injector doesn't inject fuel straight into the cylinder, but into a separate chamber, known as the swirl chamber. The chamber causes the air to circulate or swirl when the piston rises on the compression stroke, thereby improving the mixing process and combustion. Diesel engines using this swirl chamber principle are called indirect injection engines, while those which have injectors spraying directly into their cylinders are perhaps not surprisingly referred to as direct injection engines. Indirect engines generally run more quietly and can rev faster than directly injected engines. Now let's consider how the engine's output is controlled. In the diesel engine, the air supply is not restricted. Only the quantity of fuel is varied. So, when the engine is under part load, only the quantity of fuel is reduced and not the air. Unlike the petrol engine with its throttle valve, the cylinders of the diesel engine are always full of air. In turn, compression pressures are maintained, and so is the engine's efficiency. To summarize then, the diesel engine relies on compression to ignite the mixture, and its output is controlled by regulating the quantity of fuel injected. There is always an excess supply of air. Now, what about cold starting? When it's cold, a lot of the heat created by the compression is lost to the cold metal, so ignition of the fuel isn't always possible. A means of pre-warming the air is therefore required. A glow plug is installed in each swirl chamber just beneath the injector. The plugs, controlled by the engine control unit and a relay, glow red hot for a predetermined period of time prior to starting the engine. This warming of the air ensures good cold starting. The engine is ready to start once the instrument panel warning light goes out. The time for which the lamp and the glow plugs are lit is dependent on the coolant temperature. To reduce this waiting time, the system is activated by a signal from the driver's courtesy light switch on entering the car. To reduce emissions, noise and improve the idling, the glow plugs remain lit for a short time after the engine is started. Because the preheating is not required when the engine is warm, the system is switched off at coolant temperatures above 65 degrees Celsius. There's more detailed information about the glow plug system in the self-study book. Now, to review what we've covered so far, let's consider the basic conditions which the diesel engine requires to start and run correctly. Firstly, as the engine relies totally on heat for ignition of the fuel, good cylinder compressions are essential. Low compressions will cause the engine to be difficult to start, lack power and smoke. The glow plugs must also function correctly. Otherwise, starting from cold will be almost impossible. If just one or two glow plugs fail, it will cause the engine to misfire and smoke slightly immediately after starting. In short then, 4 good compressions and 4 working glow plugs are essential for reliable starting and a smoothly running diesel engine. In many respects, the 1.9-litre diesel engine's construction is similar to the 1.6-litre petrol engine we looked at in a previous video. It has a cast-iron cylinder block, aluminium cylinder head with overhead camshaft, and self-adjusting hydraulic tappets. The crankshaft runs in 5 main bearings and is fitted with a vibration damper to improve smooth running. Oil temperature is maintained by a heat exchanger type oil cooler, and a long-life multi-ribbed belt drives the alternator with integral freewheel device, water pump and power steering pump. The belt's tension is adjusted by a pulley. The hydraulic tappets have 2 movable parts, a piston and cylinder. The components are forced apart by the spring until the clearance between the camshaft and valve is eliminated. As the cam rotates and presses on the bucket, the ball valve closes, causing the oil pressure to increase in the high-pressure chamber. Because the oil cannot be compressed, the tappet functions as a rigid component, and the valve is consequently opened. A design feature allows a small quantity of oil to escape from the high-pressure chamber as the valve is depressed. This enables the tappet to adjust itself when the valve clearance reduces. After the valve closes, the cam no longer exerts a pressure on the tappet, and the pressure in the high-pressure chamber falls. The spring automatically forces the cylinder and piston apart until the valve clearance is once again eliminated. The non-return valve then opens. The high-pressure chamber is replenished with oil from the lubrication circuit, and the whole cycle starts all over again. To prevent oil draining away after the engine is switched off, the tappets include a small reservoir. This maintains a supply of oil to prevent airlocks occurring and helps to reduce tappet rattle immediately after starting the engine. Now let's return to the rest of the engine. Unlike the 1.6-litre petrol engine, which has only a crankshaft and camshaft, the diesel engine has an additional intermediate shaft. It drives just two components: the oil pump, located in the sump, and the vacuum pump. The pump supplies the brake servo unit and the valves which control the exhaust gas recirculation and idle speed increase systems. A vacuum pump is necessary because, as you know, the Skoda diesel engine doesn't have a throttle valve, and thus it creates only a little manifold depression. The intermediate shaft is driven by the rear of the toothed belt, which drives the camshaft and distributor-type fuel injection pump. The belt is tensioned by a semi-automatic adjusting pulley. Due to the diesel engine's high compression ratio, there is only a small clearance between the valves and the top of the pistons. In fact, the gap is so small that if the camshaft is incorrectly set by just one tooth of the belt, the valves will hit the pistons. It's essential, therefore, that the belt is always removed and installed correctly. But we'll look at that shortly. The clearance is also affected by the manufacturing tolerance of components, such as the height of the pistons and cylinder block, etc. To achieve an accurate clearance, and hence maintain the correct compressions, several thicknesses of head gasket are available. The thickness is identified by a series of holes or notches near to the gasket's part number. Because the head gasket selection and the setting of the camshaft and injector pump are to some extent closely related, we'll look at those work sequences next. Because here we describe the procedure for removing, refitting and setting the point of injection in one sequence, you may find that the order of events differs slightly to that shown in the repair manual. For clarity, we're working on an engine which is out of the car. If the engine's in place, which is far more likely, of course, then a little extra work is required. You'll need to support the engine and remove the air filter, engine mounting, alternator belt and cover to get to the belt. Once you've accessed the belt, set the engine to TDC on number 1 cylinder. A special tool is required to determine the TDC position if the engine is out of the vehicle. The rocker cover can be removed next. The locking bar, MP1300, is then fitted to the rear of the camshaft. To set the camshaft exactly, turn it until one end of the setting bar touches the cylinder head and measure the clearance between the bar and head at the opposite end. Halve the value and insert a feeler blade of that thickness. Turn the camshaft back slightly and insert a second feeler blade of the same size at the opposite end. The injector pump gear is next locked by fully inserting the special tool, and the belt's tension is released by slackening the pulley. Now, slacken the camshaft gear bolt by half a turn and loosen the gear from its taper by striking it with a hammer and punch. Incidentally, the gear is secured to the shaft only by a taper. There isn't a Woodruff key. The belt and gear can then be removed together, but remember to first mark the direction of rotation if the belt is to be reused. To avoid the valves hitting the pistons, don't turn the crankshaft after the belt has been removed. As the toothed belt drives the camshaft and injector pump, both components must be set accurately when refitting the belt. Setting the injector pump is equivalent to setting the ignition timing of a petrol engine when refitting the distributor. To begin with, check that the crankshaft is still set to TDC. The bar is in the rear of the camshaft, and that the injector pump is locked by the special tool. Slacken the 3 bolts which secure the injector pump's gear to the hub. Don't slacken the center nut, as the pump's basic setting will be lost and it can't be reset using normal workshop tools. We're now ready to fit the belt. Place it first around the crankshaft, intermediate shaft and injector pump gears. Continue by installing the camshaft gear together with the top part of the belt onto the camshaft. At this stage, leave the securing bolt finger tight. Tension the belt by turning the adjuster clockwise until its 2 marks align. And tighten the securing nut. Recheck that the crankshaft is set to TDC and slightly tighten the camshaft bolt. Tighten a little the bolts of the injector pump gear and take out the locking tool. The camshaft locking bar must also be removed. The engine should be turned 2 complete revolutions in the normal direction until the TDC marks align once again. The injector pump setting must then be rechecked by ensuring that the special tool can still be inserted to within 1 millimeter of the mark. If it can, then the injector pump gear's 3 bolts and the camshaft gear bolt can be fully tightened. If the tool can't be inserted, then repeat the complete belt refitting procedure again. Incidentally, if the belt is ever adjusted or the injector pump is replaced, then the pump setting, or the point of injection as it's more correctly known, must always be checked. Its setting, together with the camshaft, are critical to the correct running of the engine. We explained earlier that different gaskets are used in production to achieve an accurate clearance between the pistons and cylinder head. If, during repairs, you're simply replacing the gasket, then refit one with the same number of notches or holes. But if new pistons or a short engine has been fitted, or you suspect that an incorrect gasket was fitted in the past, then the piston projection must be measured to determine the correct gasket. Firstly, turn the engine to TDC. Using a dial gauge together with the special tool, measure the height which all 4 pistons project above the cylinder block. If the readings are different for each piston, then note the highest value. A table in the repair manual identifies which gasket to use. In this example, a projection figure of 0.92 millimeters means that a gasket with 3 holes or notches is required. Selecting the right gasket is very important. Fitting an incorrect one can result in poor starting, excessive smoke, or even the possibility of the pistons hitting the valves. For the same reasons, the cylinder head must never be refaced. And before refitting the cylinder head, to avoid the risk of the valves contacting the pistons, ensure that the camshaft lobes of number 1 cylinder are pointing uppermost, and that none of the pistons are at TDC. Finally, always renew the cylinder head bolts and pay careful attention to the bolt tightening sequence laid down in the manual. As you already know, the engine's output is controlled by the quantity of fuel injected. So let's first look at the fuel system. The Lucas distributor-type injector pump delivers fuel from the tank via a combined filter and water separator. The pump, which is the heart of the system, is a 2-part unit. A rotary transfer pump lifts fuel from the tank, and the other part pressurizes it to a high pressure and distributes it to each injector in the firing order. The fuel pressure which builds up in each injector pipe in turn is determined by a spring within the injector. The spring holds a needle firmly on its tapered seat. Once the spring pressure is exceeded by the fuel pressure acting on the needle's seat, it lifts and chatters. This action and the design of the nozzle assembly creates a fine cone-shaped atomized spray, which is essential for good ignition of the fuel. The quantity of fuel injected is basically determined by the position of the throttle lever and the control mechanisms within the pump. When the needle closes, excess fuel is returned to the pump, where it joins fuel returning to the tank. The fuel, warmed by flowing through the system, passes first into the fuel filter, where it is recirculated. This prevents the fuel from waxing and blocking the filter in cold weather. An integral thermovalve switches this recirculation off when the fuel reaches approximately 31 degrees C. Fuel then returns directly to the tank. To protect the highly accurate components of the pump and injectors, the filter must be replaced at the recommended intervals and drained periodically of any water. Under most conditions, the quantity of fuel delivered to the injectors is controlled mechanically. The further the accelerator is depressed, the more fuel is delivered, and vice versa. An internal mechanical regulator, or governor, limits the maximum engine speed and regulates the fuel delivery at all engine speeds. The pump also mechanically controls the time or point at which the fuel is injected. Basically, the higher the engine speed, the earlier the fuel must be injected to achieve correct combustion. In principle, it's the same as advancing the ignition timing of a petrol engine. A means of stopping the engine is provided by the solenoid cut-off valve. It interrupts the fuel supply between the transfer and pressure pumps on switching off the ignition. On vehicles fitted with an immobilizer system, the valve is controlled by a small electronic unit mounted under the pump. It, in turn, communicates with the immobilizer control unit and ignition key. In principle, the immobilizer system works the same as that of the petrol engines described in a previous video. The fuel system functions we've looked at so far, other than switching off the engine, are controlled mechanically. To meet exhaust emission requirements, however, a proportion of electronic control is inevitably required. The electronic control system takes care of the operating time of the glow plug system, the exhaust gas recirculation system, or EGR as it's known, idle speed increase when cold, advancement of the injection point for cold starting, and the reduction of the injection quantity at higher altitudes. The ECU manages the system and, for calculation purposes, receives input information from terminal W of the alternator for engine speed, terminal 50 of the starter circuit, the coolant temperature sensor, driver's courtesy light switch, engine load potentiometer, the glow plug voltage, and terminal 15 of the ignition circuit. The reason for advancing the injection point on starting a cold engine, by the way, is to reduce exhaust emissions. The injection point is advanced when a solenoid valve on the injector pump is energized. Lowering of emissions is also the reason for reducing the injection quantity at higher altitudes. Simply, the higher the altitude, the lower the atmospheric pressure, which in turn means less oxygen to fill the cylinders. Without some form of compensation, too much fuel would be injected for the smaller quantity of oxygen, leading to black exhaust smoke. The atmospheric pressure is detected by the control unit's integral pressure sensor. When the sensor detects atmospheric pressure below 920 millibars, a solenoid valve on the pump is energized, causing the injection quantity to be reduced, and in turn, the emissions. To reduce the exhaust's HC and CO content, an oxidization catalyst is fitted, details of which can be found in the self-study book. To reduce the NOx emissions, the engine features exhaust gas recirculation. Under certain operating conditions, the system recirculates a proportion of the exhaust gases to lower the oxygen content and, in turn, the combustion temperatures. The system's operation depends on engine speed, load, and atmospheric pressure. The EGR valve is controlled by the solenoid-operated vacuum valve, and the neighbouring valve controls the idle speed increase actuator. The final role the electronic system plays is that of controlling the glow plug circuit. To control the system, the ECU considers the coolant temperature, whether the ignition is on or the starter is operating, and even the number of times that the driver's door has been opened. Incidentally, the glow plug circuit is protected by a 50-amp fuse. The adjacent fuse is for the solenoid vacuum valves. Finally, there's one component whose function we haven't yet explained, the engine load potentiometer. It provides a variable voltage signal depending upon the accelerator's position. The signal is used by the ECU to influence the operation of the idle speed increase, the start of injection point for cold starting, and the EGR system. Adjustment or separate replacement of the potentiometer isn't possible, so do not slacken its mounting screws. Similar to Skoda's petrol engines, the diesel engine's electronic control functions are monitored by a self-diagnosis system, which can be interrogated using the VAG 1552. Once the diesel engine's address word, 41, has been entered, these functions are available. 02, interrogate fault memory. 03, final control diagnosis. 05, erase fault memory. 08, read measuring value block. And 06, end output. When problem solving, it's best to check thoroughly by progressing through all the functions. You're probably already familiar with the 1552's operation, and in principle, its use is no different on this engine to previous petrol engines. But there are just one or two points to note. Although on this particular engine, final control diagnosis can be initiated with the engine running, you'll find it easier to hear components working if it's carried out with the ignition on and the engine stationary. Final control diagnosis checks the function of the EGR valve N18, glow plug warning lamp K29, glow plug relay J52, fuel injection quantity valve N194, idle speed increase valve N177, and the advancement of injection valve N108. If a component fails to operate, then further testing of the circuit must be carried out before condemning the component. For detailed information on all the self-diagnosis functions, including reading the measuring value block, refer to the repair manual. The glow plug relay and warning light are checked in the final control diagnosis function. However, to confirm that voltage is actually reaching the glow plugs, connect a test lamp between earth and the terminal strip. The lamp should light when the relay is energized. If it doesn't and the relay doesn't work either, then check the simple things first, such as the fuse. There are several ways of checking the glow plugs themselves, depending upon the work which you may be carrying out at the time, so we'll describe all of them. To check the continuity of individual glow plugs, first disconnect the terminal strip from each plug. With an LED-type test lamp connected to positive, touch each glow plug terminal in turn. A defective plug is indicated by the lamp failing to light. An alternative way of checking the glow plugs is to measure their total current consumption. By comparing the current against a table in the repair manual, an indication as to how many glow plugs are working can be made. By the way, if the injectors have been removed, then it's simple to test the glow plugs. First, remove the connector from the temperature sensor. This tricks the control unit into thinking that the engine is very cold, enabling the plugs to operate for longer. When the ignition is switched on, you should be able to see the glow plugs glowing. Remember to refit the temperature connector afterwards and cancel the ECU's fault memory using the VAG 1552. If on removing a glow plug the end is found to be burnt, then it indicates that the accompanying injector is faulty. If the injector isn't repaired, then serious and expensive damage to the piston and combustion chamber will occur. Before removing injectors, clean the surrounding area, particularly the pipes. Absolute cleanliness is essential, as just one small particle of dirt entering the fuel system can damage components. Having unscrewed the injectors, it's always best to test all of them, by the way, lift out the heat shields. The shields, which protect the end of the injector and form a gas-tight seal between the injector and cylinder head, are crushable and therefore must only be used once. So always fit new heat shields and make sure that they're inserted the correct way up. To test the injectors, the VAG 1322 is required. Serviceable injectors produce an even cone-shaped atomized spray without drips. The injector should spray or break at the correct pressure. Pump the handle slowly while watching the gauge. A braking pressure of 130 to 138 bar is correct for new injectors, and the wear limit is 120 bar. Finally, test the nozzle for leaks. Slowly press the lever to maintain a pressure of about 110 bar for 10 seconds. No fuel should leak from the nozzle during this time. If the only defect is with the injector's braking pressure, then it can be adjusted by exchanging the shim of the spring assembly. A thicker shim will increase the pressure and vice versa. However, if the injector's spray pattern is suspect, the nozzle drips, or you're in any doubt about its condition, then always fit a replacement injector. And remember, when overhauling injectors, absolute cleanliness is essential. There's an important safety point to be observed when testing injectors. They must only ever be sprayed into a closed container. Never place any part of your skin near the injector nozzle. The high-pressure atomized spray will penetrate the skin, and the consequences can be fatal. Other than a burnt glow plug, further indications of a defective injector are misfiring, engine knocking, loss of power, excessive black exhaust smoke, increased fuel consumption, and increased blue smoke on cold starting. A faulty injector can often be identified by running the engine at a fast idle speed and slackening each injector union in turn. A suspect injector is indicated by the revs remaining the same or the engine knocking disappearing. From a routine maintenance point of view, the only items requiring occasional checking are the idle and maximum speed settings and the draining and replacement of the fuel filter. The idle speed is regulated here. Do not on any account turn this screw. Because the alternator is fitted with a freewheel, the engine speed must be measured using the VAG 1767, which records the speed from the flywheel and not by using the 1552. The engine's maximum speed without load is regulated by this bolt, which is covered by an anti-tamper protective cap and seal. To check the setting, briefly fully open the throttle and note the revs. If necessary, corrections can be made by turning the bolt, but remember to replace the cap and seal afterwards. The fuel filter, which requires draining of any water periodically, must be replaced at the recommended intervals. To prevent airlocks after exchanging the filter, always fill it with clean diesel. On occasions, you may also need to bleed air from the pump's inlet pipe by filling it with fuel until all the air is expelled from the bleed screw. If available, a vacuum pump incorporating a small tank can be used to simultaneously fill the filter and bleed the system. And now for one final point concerning the fuel system. For the engine to run correctly, the system must be free of air. Unlike fuel, air is compressible. Air bubbles in the system will cause erratic running and can prevent the engine from starting. A hose which is slightly loose will often permit air to be drawn in without fuel escaping. To help prevent such problems, regularly check the security of the hoses and check that the filter's thermovalve O-ring is not accidentally damaged. Diesel power is a completely new venture for Skoda, and the technology may also be new to you. We hope that viewing this tape and reading the self-study book will help to remove some of the mysteries about an engine which, in principle, has been around, like Skoda, for over 100 years.